So good morning, everyone. We are going to switch gears a bit today now in this talk about understanding how to do or what it means to do system research, right? So understanding where systems are in place today, let's go back to something that every one of us knows. So who all watched our ICC World Championship trophy match on Hotstar or Geo Hotstar like a month back? Right? And did you see that on the right hand side corner of the screen, they were showing how many people were simultaneously watching this match with you? And did you just get on the number of what the scale at which they were handling the traffic or handling your viewership, and in such a way that there was no drops in any of your viewership. There was no buffering happening for any of you guys, right? So it was the same experience for me. And then I tried to read how did they actually go about and build such a system that would support such a huge traffic in place, right? So in that sense, we know they came up and built a very scalable system designed to support such a huge traffic. Basically, it was a web application that was supporting these such a huge traffic, right? So web application is something that a lot of us kind of keep on building day in and day out sometimes in our projects as well, right? So what do you use or what do you mean by a simple design of a web application? There will be a client sending requests to your front end. There will be a backend service, and that will be talking to your database or a data store, which will be having or storing the data, right? So this is kind of the system that you guys kind of build. Now, I want this talk to be more interactive than me just talking. So if I wanted to make this simple system scalable, what would be your approach, right? What would you have done to make this system scalable, right? I want answers from you guys. Yes. Okay. Redundancy backend, right? As we said, we had to add redundancy to scale these systems. So you add more replicas to each of these services, right? And once you add more replicas, you need something to distribute your traffic equally or with some logic to these backend services. You need something called as a load balancer in front of these services. Right? This is a simple system designed to scale your application. And what these guys also had was a cache or a CDN kind of sitting towards the client side so that they could cache the requests that were coming in and could handle it closer to the client itself, right? So this was kind of the basic architecture that systems like Hotstars, which actually handled such a huge traffic, could also build upon, right? And obviously, when you build on such a large scale, they had to support a lot of infrastructure to do that. They almost had around 400 nodes to be supporting such a huge traffic of our requests going to them. And that's where they required something called as an orchestrator or something to scale this system well, right? So that's where they used Kubernetes as their orchestrator, which ran applications in terms of pods, which ran application inside the pods on these Kubernetes environments, right? So this was kind of the basic architecture of Hotstar's scalable design, right? But what they saw was once there was traffic coming in, they monitored the traffic going in, and they saw there was a lot of uneven traffic going in to these applications. They measured the traffic going in, and they thought this is not good because some nodes are getting huge traffic, some nodes are not getting good traffic. We should see how we can even out the traffic that's going to these applications. And that's where they thought we'll have to scale evenly. And that's where they thought it would not be making sense to just scale more nodes to Kubernetes in one Kubernetes cluster or one Kubernetes environment itself, but scale it across multiple clusters or multiple Kubernetes clusters so that once they have more nodes, more Kubernetes environments, they could evenly distribute traffic across the nodes and the Kubernetes environments itself. And they brought down the traffic distribution to not be just haphazard as in the left side, but a more even out. That is not 10 Gbps traffic going to one node, but 2 Gbps traffic going to all the nodes or all your cluster environments, right? So once we scale the microservices, as we talked in the last slide, then they scale the infrastructure itself to support the huge traffic, right? There were some other nitty-gritties that they did and scaled down how they handled the IP addresses so that even distribution happens, how they created the private network so that there was security across how the requests were going to individual nodes as well, right? So there were a lot of internal details, but at the high level, the design was this simple. And that was a base of something that we'd use day in and day out, like any OTT platform or that we have been streaming or using as of now, right? Now, that's where you know that you need to have a system engineer or a system researcher in place, because without them, these systems wouldn't have been built or been sustainable in such a huge environment or huge traffic or huge population that's using OTT platforms or any web app or your phone apps nowadays. With that, just one insight, and this was something that got published in a Uber paper. So I spoke about a Hotstar example, but the same thing applies to a lot of our apps as well. So Uber also said that this is kind of the map of the microservices that they run, right? So you can see the amount of microservices that they have deployed over the entire infrastructure to support our traffic, right? So you can see the scale at which these applications run, and that's where we as researchers can contribute and make these systems run better. So taking a step back, as we saw a graph there where we saw the traffic not going well, and then they scaled that infrastructure to make the traffic go on evenly. How did they do that? Was through efficient monitoring. So what do we mean by monitoring is measuring your system, if it's running well or not, measuring its resource, if it's running well or not, right? So for that, there are a lot of solutions in the market today which do help you do efficient monitoring, right? So there is something called as Prometheus, which runs on your Kubernetes environment, lets you measure metrics at various levels. I'll have a question for you guys on this later, but they'll measure metrics very well and just print out on your dashboards what's going well or what's going not well per metric, and you can zoom in out at various levels. Similarly, there is something called as Instana, which helps measure your logs or your traces that way. That is, trace in the sense when you write an app, you want to see if there are a microservice chain, if the microservice requests are going well in this microservice chain or not. So you can use these traces to understand if the requests are going well or not, right? So this is one kind of observability solution that can help you do these tracing well. The third solution is log DNA, which is the third kind of observability that you will have in your system, is to understand if the logs are being collected. That is, in your simple cases, you put print statements if, okay, it's going into this function or not, is kind of a log that you're actually adding in your system, right? So if you're these are the logs that you understand if your system is running well or not, or just to print out or help you debug whenever there is an issue happening. And so there are these solutions in market today being deployed on your Kubernetes environment. But what happens is, once you scale across not just one cluster, across cluster, you want to collate metrics from across these environments, it becomes very difficult to manage and analyze all these metrics, all these data across these clusters, right? And the cost of these storage and maintaining all these metrics or observability data also becomes huge. Right? So we call it an observability tax because it's a huge tax on anyone maintaining these infrastructures. Right? So we have a solution in place to help minimize these costs, and not to just minimize it naively, but doing it a bit intelligently. That is, analyzing that what metrics are important and what metrics can help any analytic downstream tasks that run on your system, so that you don't have a standard frequency, right? The solutions that I've just mentioned in the last slide have a standard frequency for all these metrics. That is, every metric gets sent at 30 seconds. But that's not what analytics functions need, because all metrics have a different importance. So you need to be able to have a tunable knob that can work at a per metric granularity as well. And that's where our system came in. We sat with your metric generator or metric producer, that is here the metric collector, and it could modify or do the transformations at per metric granularity before it being sent into the public cloud or the global cloud or the central cloud where the analytics run. Right? So we did that at the closer to the metric collector to reduce the overheads of how much traffic gets sent for the observability itself across these clouds as well. We also open source this code and it's available. You can check out the repo, you can fork it, open issues and try this out as well, right? So with this, I want to conclude on this a part of the talk that observe smartly with managing less so that it's done efficiently, right? With this, because I talked about open source.
Can you give an example of what are these transformations?
Yeah, so just there can be multiple transformations like filter some metrics at like only 5 metrics of last 10 seconds just send, or just aggregate after a minute and send, or just adapt if there is a risk level is high, then send it more at 5 seconds frequency. Just rest metrics can go at 30 seconds frequency. Like if there is a node issue, you can send it at a high frequency. That kind of transformations. So I want to conclude on this area with the point that we open source this code, and this is something that's very important in today's area. That is, you guys should, maybe if you're working on a project, just open source it, right? It helps connect with people, helps garner more interest in the work that you're doing. So I'll just highly motivate you guys to open source whatever work or whatever project that you guys are working on. So we said we monitored something. So I want to ask you a question. I said resources are being monitored. So what are the resources that we monitor? So you measure resources like CPU, memory, storage, right? And there are a lot of things that you can do once you measure that. But now that we've been talking about LLMs for a long time, what are these guys? What these pictures make you think about? Yes, so these are kind of GenAI or LLM models that are being used widely now. But now that we spoke about resources, what is the main resource that backs these models? The GPU is kind of the core resource that helps enable running these models at such large scales or running such large models. Right, so I think Natarajan showed about this pipeline. There was a data preparation step. This is kind of the typical pipeline for any LLM workload, but it ends on what is called as deployment. But there are things that can be done at the application layer, which Natarajan spoke about. But there are things that go below that, for deployment as well. Right, when you run a training model, it cannot run on a single GPU. You have to run on multiple GPUs. How will you distribute or how will you send it across multiple GPUs is a question that a deployment engineer or someone who works on the lower layers of your stack for running your LLM models require, right? So there are a lot of open challenges in terms of not how the model is running, but how the model is running on your system as well, right? So there are things, system aspects where we spoke about resources like memory, the compute like CPU or GPU, how they are best optimized to run your application is very important for running these models efficiently, right? So these are kind of very open challenges that are lot of research work has been going on to run these well. So one thing that we've been coming upon in our yesterday's talk as well is DeepSeek. Right, so we thought there were models in place already, and DeepSeek came in and like revolutionized. Oh, we could do a lot of things, and we are much better than other models. But in terms of what, right? So they said they were better in terms of how they were using their compute, or they could do their computations in much lesser resources. And there is a good paper on DeepSeek which talks about what kind of system optimizations they put in place to let them do that, right? So I'll talk about two of them in today's talk. One is around parallelism, how they efficiently used parallelism to improve their model performances, and how they improve the networking itself to improve the performance. So before going in depth, just a high level picture of how your GPUs work today. If you have an NVIDIA GPU, you be using CUDA as your primitive to talk to your GPUs, and internally what they have is what is called a streaming multiprocessor, which is kind of the smallest programmable unit. And internally it has what is called as thread blocks, which are basically threads that are performing the same operation. That is, all threads are performing the same operation, that is called as a thread block. And thread blocks, 32 threads kind of form one warp which you can actually execute or give instructions to run on, right? And if it's assumed that all these threads in that warp will execute similar operations, and if there are some divergence, there is a hardware notification that it comes in that the one thread has got divergent and it's not working well, right? So the conclusion is there is the smallest unit, that is essence, that you can program and run on. And the second concept that I would like to highlight around is parallelism. I spoke about that. You cannot run your training model on just one GPU. You need multiple GPUs to run your training model. So you need to efficiently use, or how efficiently use these multiple GPU models, right? And how you can do that is using good parallelism techniques. So there are multiple ways you can do parallelization across the GPUs. So one way is you can split your data itself, the training data or your tuning data that you're getting, you can split it across multiple of these GPUs. That's one technique. Like these are working in tandem, right? These like this is not that you just use one of the parallelization techniques. These techniques in combination make your LLM or your workload to run well, right? The second kind of parallelism is model parallelism, where you split what you call as the weights in your model itself, right? So each layer has a lot of weights that get computed. You can split them vertically so that they can be split across these multiple GPUs and they can compute their computation itself, and then you can merge them after the compute is done, right? So at a high level. The third is pipeline parallelism, where the architecture consists of multiple layers, right? You can split the layers itself across multiple of these GPUs, and you can let them run parallelly, and then you can merge them to get the output. So this kind of is a pipeline parallelism that happens. But in pipeline parallelism, there are issues that are kind of bubbles happening. That is, if you run you run a model, run one layer, you're waiting for the other layer. That should not happen. So there are ways in which there are techniques in which these optimizations have been done, that the bubbles or the weight gap between these techniques, these layers is reduced, right? And that is done using efficient configurations on what batch sizes being shared, used for each of the layers, right? So these kind of techniques are used to efficiently use the GPUs in the, by parallelizing or splitting your data, splitting your model across multiple of GPUs. The third thing I spoke about is networking. That is, they optimize on networking because, as we said, we had to use multiple GPUs. There were optimizations done on how GPU to GPU.
Yes. Sir, one clarification.
Yeah.
What was the difference between pipeline parallel and model parallel?
Model parallel, the weight was split, and pipeline, the layers itself. It's horizontal versus vertical split. So the third thing we spoke about is networking, how you can optimize the networking itself. There are a lot of techniques that NVIDIA had put in their GPUs to improve the communication. So one kind of communication is GPU to GPU communication. Another is there won't be a lot of GPUs in your node. You have to also communicate across nodes. So there has to be optimization on how these communication across nodes as well happen, right? So one is how the GPU and the NIC can communicate faster way. They can have a shared memory that can be used, where the GPU, once the compute is done, put the data in a shared memory that can be picked up by the NIC and shared across the NIC as well, right? So this is one kind of technique that they've put in. There is things like peer-to-peer networks, that is two GPUs itself. There is a protocol in place to improve the communication across your GPUs as well, that has been done. And there are things like direct IO kind of thing that we have been using traditionally in our computer networks to optimize our communications. You do a direct IO kind of thing to communicate with the GPUs as well. Right, so there are things in place to optimize your network as well. So just coming back to DeepSeek, there were things that I spoke about, that did efficient parallelization, did efficient networking. That is, they co-communicated the user networking well. That is, if there was some GPU to GPU communication happening, they used that time itself to do a cross-node communication itself, and they proposed a dual pipe protocol or algorithm which helped them run their communications in parallel with their compute itself, right? So you don't waste time on these networking or these communications. Your compute is running in parallelly. So in that way, they optimized on the time or the wait time that these applications were seeing or these workloads were seeing, right? So these all challenges are at the lower layer of your stack, that is your systems or your memory or your compute or your network. Right? And obviously, there are a lot of these optimizations that DeepSeek put in place, but they are not the end. There are a lot of optimizations that we can think of, that we can do or we can propose on our own to the lower layer of your stack as well. So coming back to what we are working at IBM Research, so we see that GPUs are in place, are kind of readily available now, but they are being used a lot by your LLM applications, right? But they need to be efficiently used across your applications. And now, as you said, you have your data center in your institutes as well, which you are kind of sharing across sharing across your individuals that way, right? So this needs efficient management of these GPUs that are being used in the infrastructure, and something like these platforms that have been there traditionally will be in place in your institute as well to use these GPUs efficiently, right? There are LSF, Slurm, there are multiple examples of it, Kubernetes being the most famous of this because it's being used for microservices or cloud environment as well, right? But these lack what our Gen AI workloads need, right? So they don't do efficient GPU sharing. What I mean by efficient GPU sharing is once you ask for a GPU, you get one GPU. Even if you're not using it 100%, it's kind of dedicated to you. And other user comes in and asks for a GPU. If it's not available, he or she won't be able to run their workload, right? So we need to efficiently share the GPU so that they can run in isolation on the GPU, and a lot of people can use that limited GPU resources that are available in your infrastructure, right? So how to the infrastructure manager or your platform engineer or your platform should manage how these sharing happens across multiple of users efficiently, right? The second thing is something that a lot of you might have also experienced if you're running LLM workloads, right? You run out of memory most of the time. You get an out of memory issue a lot of time. So it's because memory is a major bottleneck of running these LLM workloads, and there are a lot of open problems that can be done or that can be worked upon as system researchers to efficiently manage how memory is being shared, how memory is being used, how memory can be isolated across applications to run your workload well, right? So that you don't run out of memory when you run your application. And of course, it's the application that are running, that is the LLM workloads, as we spoke about parallelization, they can be really well parallelized compared to what other applications or the traditional applications that we've been running till now, right? So we have to efficiently use these parallelization techniques, or the platform manager or your where you're running your application should be aware of how these parallelization techniques can be efficiently used to run your AI platform, AI workload that way, right? So with that, I like to conclude by how you can get started, right? I spoke about two things. One is doing your web application, building a scalable system. Second is how you actually can use, there are layers on the stack when you are running your LLM workload itself that require system research, our system engineers to run them efficiently, without which the applications get stuck or get bottlenecked by your resources, right? So try running your workloads, try measuring your workloads that way. It's not just getting them running is enough. Understand, run the measurements and understand why are they getting stuck, what is the issue that they are facing, and think about scale that way, right? So one thing is, once you realize they are being stuck, what you do is add more resources. Adding more resources is one way to scale your system, but it's not the only way, right? There is a limit of how much you can scale. So you should look for problems on optimizing the existing resources itself, so that within your existing resources itself, how well you can run your application, right? So that's what kind of becomes a system research as well, because there are optimizations that can work not just for you, but a lot of other people that as well, they can leverage your system or your optimizations and better build their systems or run their applications, right? So what kind of optimizations you can look for? This is just a starter. You can look out for recent papers in system research. There are top conferences which talk about the optimization that you can use, you can incorporate. In fact, most of the research labs or most of the companies today use these research papers as the base to pick up system optimizations that can be incorporated into your systems, and they really see good improvements because of that, right? So optimize, scale, measure your system, and that's how your research journey in systems will start. With that, a bit around our hiring. We are hiring in our systems research group, our platform research group at IBM Research India. Do get in touch with me if you are interested. We have research opportunities as well. We have summer internships, 3-month summer internships. In fact, and our applications go out in August and so around August and September. Do look out for my post on our internship programs. We also give out a list of research problems that we are kind of trying to work in the next summer. So if you are writing some of the research problem, get in touch with the mentor who has put out that problem, and you can connect with us and work on that problem as well. And because I'm a diversity lead at IBM Research, we have a yearly diversity connect for students as well around September. So follow me on LinkedIn for that as well. And we hope to see you at IBM Research just to get a feel of how research is done at our lab. With that, thank you for the talk.
Oh, hi. I have a question in the observability volume manager. So in your architecture, would certain microservice metric that is being observed and the fluctuations in those have a priority filter? Like if there's a microservice change and some certain metrics is actually affecting the chain downstream, but it's not an issue right now, but some metric that needs to be improved further as during consolidation of the whole metric. So is it being filtered directly at individual metric level, or how is it working?
So that is also a way in which we give the flexibility, right? So we talk about a metric level, we can go down to a metric level, but we can go down to a microservice level as well. And as you said, can be priorities given, right? If there is a microservice which is talking to, say, 5 microservices, so that going down can impact like 6 others that way, like including it. So if that is a metric, that is a microservice that going down, then we can improve the granularity for metric collection for that microservice itself. So we can go down to a metric level, but the metrics can be for a microservice level or a cloud level or an edge level as well, right? So that is the tunable knob that we provide.
Morning, ma'am. I have a very basic questions. Like suppose I am developing some systems, but I don't want any human intervention to look into the matrices or the logs. So what I want, I want integrate LLMs to it, so that I do not have any system developers who is debugging that. So it is kind of self-healing systems what I am looking for. Okay. So how you are going to integrate that into the servers so that they are going to recover their debugs itself by themselves?
Okay, so we can talk offline as well, but the architecture that you will follow is kind of a closed loop system where you will need some installations at per microservice level or pure Kubernetes level, which is collecting the metrics, sending it out to your analytics engine. The analytics engine will throw out that this is the issue happening. Then there would be some standard issues that are identified. Then you will see, okay, if the CPU is going out, just scale it vertically or add more CPUs or just add one more replica. So that kind of standard definitions are there that can be defined, and that can come down to remediating it in the actual system. It can be a closed loop that way.
My second question would be like how you are preventing the DOS attack that your going system have. Like maybe you have given the example of GeoHotstar. So there may be some.
Sorry, I didn't get.
You have given the example of GeoHotstar servers.
Right.
So there may be many DOS attacks that are going to happen on the servers. So how you are going to prevent that?
Yeah. So one thing I spoke about is you create private networks so that your traffic doesn't go in, or you have what is called as a DMZ zone, which actually filters your packets or sees if there are a lot of packets coming in, just drops packets, sees if it's coming from the same IP address or not, drops at that level. There are a lot of policies in place, IP policies or network policies is in place to drop such and prevent such DOS.
But there can be some multiple IP addresses, so like.
Yes. So you identified range. They are called as bots, which can come up anywhere in the system. So you kind of learn what kind of the bots are coming in, what kind of traffic they are kind of generating. There can be a similar kind of packet or payload that they are generating. These are just techniques in which you can identify these traffic.
Are you integrating the rate limiter there also? Like rate limiter number of requests?
Yes, that can happen at a lower layer. Like at the microservice level itself, you can have a rate limiter so that such a request cannot happen. That is at a higher layer of the stack. At the application layer, you can prevent that. Okay, only 100 HTML requests can be going into a microservice.
Thank
that kind of rate limiting out.
Yeah. Good morning, ma'am. My question is, what are the current challenges in the system research and how we can effectively address them? And the follow-up question is that what is the role of artificial intelligence and machine learning in system research in perspective of jobs?
Okay, that's yeah. We can talk offline as well if I think if we. Okay, okay. Yeah, so I understand there is a lot of curiosity and a lot of tension that if you're not doing LLMs, you're not using LLMs, you won't have a job or you're not doing relevant work. That's not the case. I understand the applications have been there for a lot of years. There have been microservices that were been deployed on cloud. LLM is kind of a use case or you can consider them as application. Lower layer, there are resources. At the end, there are resources that are they being hosted on. They need some resources to run on, right? So it was CPUs that were critical for your microservices. Now it's GPUs that are critical for your applications. So you can look for lower layer of the stack to understand that, okay, is my GPU working well? How can I improve it? Is my communication across GPUs working well? How can I improve it? If I'm deploying it on a Kubernetes environment, what are the challenges? Because GPU is kind of a new resources for these environments, right? So they are not kind of adopted or having the flexible knobs that they had or they had improved on when they were running resources like CPU, using resources like CPU and memory. So are there optimizations I can do for that as well, right? So that kind of opens up some system research problems in this area. And going forward, there will be other applications that can come in. The story might change, but the underlying system research will be required or will keep running. Just the resources might change or the way you're doing, what resource you're using might change. But the system research or the concepts that you've been using, the OS courses or the networking courses that you've been taking in your undergrad or postgrads would help you build these systems well. These won't go.
Thank you, ma'am.
Hello. You talk about logs. Logs are huge and they also eat a lot of storage also.
Yes.
I want to ask how to in efficiently way we can analyze these logs and generate some alerts in real time. Means that's sometimes we face issue.
Yeah. So I didn't talk about it. That was work done by one of my colleagues where what they are doing is they are summarizing the logs itself, that is picking up metadata from the logs itself, and based on the metadata generating metrics that can be used to generate alerts that way, right? So there are work on that. I can talk offline on that in detail.
Okay, fine.
I have a question regarding the observability. A lot of applications, Kubernetes and all, they don't have the observability part of it. Some standalone solutions like provide the observability metrics. So observability is getting attention day by day. So are you thinking about that we should integrate the observability as an in the design of the systems?
Yes. I'll say it in a I spoke about a very general observability, but whenever you write a simple application itself, right, the first thing that you see is the correctness, that is, it's serving your request well. The second you see is how much you can scale or how much resources it's consuming, right? You run a top or just see how much memory it's consuming, how much CPU it's consuming that way, right? So the observability actually we kind of use observability in a very raw form in any application or any system that we build, right? So I won't say observability is becoming hot. It has been there and will be required for any system or a basic microservice or a basic application you build as well. The way you do may change based on your deployment type, but your observability has to be happen, or some measurement, some performance analysis, some performance measurements or analysis is required.
So this was sort of, I think, related to what Nagarajan had spoke earlier as well. So a lot of code optimization today, like refactoring or making it more efficient, can happen via LLMs also, right?
Yes.
So now the question is, there's still some part of performance optimization is also a little bit of like black magic. You have to look at the underlying hardware, what runs, what doesn't run. Yes. So how much of this, like what you're seeing in industry, can be automated via LLMs or something, and how much of performance optimization still needs human intervention, that some performance engineer, the one that you wanted to hug in the slides, right? Mm-hmm. So some performance engineer human intelligence is needed for performance optimization. How much of that is the case, and how much is can be done by LLMs today? Do you have a sense for that?
Yeah, so as of what we are seeing, it's not there. We really need our human, first manual effort to understand what's happening wrong, because there are a lot of layers in the stacks which are still being in building, right? The compiles, the graphs are being rebuilt, the graphs have to be optimized. So that layer, there is no LLM being used as of now. But maybe in future, once these processes get streamlined, maybe we can incorporate some LLM techniques to improve that. But as of now, nothing is there in place to do that.
So, just a quick question about the platforms that you are and some examples of tools that you were mentioning. Have you had some experience with doing non-NVIDIA GPU work? Because we've been trying to probe some stuff with AMD and seems a little more open for doing system engineering work with GPUs.
Right.
So, is there any kind of a
yeah, we do. I can talk to you offline, but we have a IBM AI accelerator chip that's coming in this year. So we are working on the stack for it and seeing what works or what not works, what layer, how the networking can be optimized for AI applications itself. So there is work in that we are doing parallelly along with what we are doing. And the platform that I spoke about, there is a FMS HF tuning. It's an open source repo that's built by IBM, which is done as a platform to let you run your tuning models efficiently. That is all the optimizations in place to run your tuning models efficiently.
Yeah, which is, of course, I'll look that up too.
Yeah.
I was just wondering about lower layers in the sense that, there's a lot of plumbing in the memory management layers, the drivers, even the SM schedulers,
Yes.
which is really opaque from the NVIDIA story point of view.
Correct.
And I think AMD drivers let little more access into all of that things. And one view of systems is, of course, to have the end-to-end plumbing, but at the lower layers, I was wondering if there's more experience or if you have any other take on, which platforms should, for example, students be working with, because I think that also exposes a whole bunch of inner details of what's.
So we also, so this is how you get access to, we generally work with NVIDIA GPUs till now, so we couldn't go into that layer of things to see if we can optimize that way. But I think as academic institute, we can look out for opportunities where we can run at that layer or see problems, open problems there.
Thanks.
I have a question on my student's behalf. So he's working on MLSys, but he is not well. He's listening live stream, so he will hear your answer also. So he's been actually trying to, do this model parallelism versus data parallelism, measure the latencies. We are trying to do exactly what your last slide said, measure things, find the problems to solve. So, so he's saying you explained, data parallelism, model parallelism, talked about latencies, but not how you measure these latencies individually. So the layers are done in sequential order, data is being passed from one GPU to another, there are latencies which you are trying to maybe do some other work in and so on. So I think he's asking you about the instrumentation tools and so on that you might have used.
Yeah. So some things like we were using NVIDIA GPUs, so there are something like NVIDIA SMI got us the utilization sense that way, right? And if your workload is something like a training or a tuning job, there are something called as a trainer controller, which splits out how much time it took for each stage or each epoch of your application. So in that sense, we collated that and
so there are
NVIDIA SMI also splits out the memory that you're being using for your application. So and it can vary with time. So you can plot a graph and see how much.
So you do get direct measurement. You're not like doing estimations or anything.
Yeah,
we
have a work which one of my colleagues is doing on estimating. So because these training and tuning jobs are long running jobs, just estimating how much time will it take. So do you understand how much resources need to be allocated for this job? Is kind of a work that we are actually parallelly doing, and for that also the data that we are getting it is from prior running doing multiple runs of these data on various heterogeneous hardware and getting these numbers.
Thank you. We'll take it offline after this thing.
Thank you, ma'am, for such a wonderful talk.